So in this video, we're going to learn about Lesson 3 of the Spatial Viz app, which is on orthocubes. So we learned a little bit about 2D plan views, and in our isocubes, we produced an isometric. Now, orthographic projections are actually two-dimensional views. And so you see the 3D shape on the left-hand side. That is your isometric, and it's using isometric grid paper. And what we want to do is, can we produce 2D projections or orthographic projections, which are shown on the right-hand side, that help us understand what does that object look like from its right side when we're looking at it from the right side, when we're looking at it from the front of the object, or if we rotate it and look at it from top down, or the plan view. So on the right-hand side, you see our 2D orthographic views. So we rotate an object so it's at right angles to the plane, and we can see what the projection looks like. That's the right side view. If you look at it, that's the front side view, and that's the top view. So again, importance and use of 2D drawings. 2D drawings are important. So, we mentioned why 3D drawings are important. It's good. Our whole world is in 3D space, but, 2D views can really show a lot of sort of range of motion in a plane. So this is in art. Architects use a lot of 2D views to demonstrate floor plans or show where the door openings are, or help us identify flow, or how to construct a particular object. So understanding how to take a 3D object and show it in a 2D view is extremely important. Now, why are dimensions drawn in our 2D view instead of on the 3D view? And the hint is, what did we learn about properties of isometric drawings in the last lesson? So if you recall, in the last lesson, in the isometric, we asked if the diagonals were true to scale in the isometric view. And so what we learned is, sometimes in the 3D view, some of the dimensions aren't really represented to scale. And so in 2D, they're exact. And so that's where we always put dimensions on the 2D views rather than on the 3D isometrics. So again, if you recall that in a 3D drawing, the line lengths aren't guaranteed to be true to scale, but in 2D, we know for sure that the diagonals are equal, even though they don't look like it in the 3D isometric on the left side. So let's talk about how we align our orthographic projections, the views. So we start by the glass box approach. And this theory is used to help us kind of see how the different projections of a 3D object that's inside of the box, how does it end up looking like in a 2D face. So if you place an object in a glass box, then all the planes that are parallel to it are what we call the principal axes of the object. And if you project those planes, if you project the object onto those planes, you get what we call the orthographic projections. And so we align these three principal views. The three principal ones we use in the US, third angle projection. And so what we do is the three views that help us define the shape of an object are the front view, which is on the bottom left, the right side view, which is over to the right, and the top view, which is up top. And we align them like this. So what dimensions each of these views give us, the top view will give us the width and the depth of our object. The front view, or the green one, will give us the width and the height of the object, and the right side will give us the height and the depth of the object. So having these three principal views allows us to form the full 3D object just from these three principal views. And we use what we call miter lines. So this is called third angle projection, and we use a miter line. It's basically a 45-degree angle line from our object, and that's how we make sure everything is aligned appropriately. So we align them according to how the glass box unfolds, and it's called third angle projection. And so when you draw these, then make sure that the dimensions from the top view and the right view are the same. So we want to make sure that we start drawing the top view the same distance away from the front view as we draw the right side view. So distance A is the same in both of those directions, and then we have a 45-degree angle or line that helps us project the views. So again, the aligned views share a dimension. We said that the top and front views share one dimension and the front and right share another. And if we do not align them, then Some of the ones that aren't aligned, like the top and the right side views, they're related by the miter line. So it's a convenient method for drawing other views. So once you complete one view, you can help draw the other views by relating the dimensions together. So the app goes through this a little bit to teach you how to do this. One important concept to introduce is the concept of hidden lines. So hidden lines are often lines or changes in something happening in the object, but you can't really see it. So for example, look at the right side view, which is the blue face in this object, okay? When you're looking at the blue face, you expect to see that blue shaded area. But behind the scenes, there's a change in elevation in the object. So behind the blue face, the object changes elevation at that hidden line. And so instead of putting a solid line there, you put a dotted line because it's not something you can actually see. It's happening behind the scenes. So we draw them as dashed lines. So one thing to note is that when you have a solid line overlapping a hidden line, the solid line is always drawn. So let's take a look again at the right side view, which is over here, okay? When you're looking at the right side of this object, you're looking at it from this direction right here. So what you see is you see this rectangle right here, and then you see also this rectangle right here. So this is what your right side view looks like. There's a rectangle and there's a line that indicates there's a change in depth here, and this one's pushed back a little bit. But what we also have behind the scenes that we don't see is that it goes back to going to one cube high over at this location. And so if we didn't have this object here, we would see that this is a hidden line. So we would also have a hidden line over here as well to indicate that there was something going on back here that changed the elevation. But since we already had a solid line right here, we don't need to show the hidden line. And you will learn this other view, the front side view, kind of gives us what's going on behind the scenes over here. So by having multiple views, you're able to replicate the entire 3D object. So the way we draw dashed lines in the app is that we have a little intersection at the grid. Every vertical line will have an intersection, and then we fill it in with a small dash in between. Okay, so it's really important when you're in the app because people get a little frustrated with these hidden lines, but if you need to zoom in and very carefully make sure that every time you have a vertical line that where you want a hidden line, you draw a little dash at those vertical lines, and then you make sure you put a little dash in between. So again, hidden lines or dashed lines touch at the edges, or they intersect the solid lines. You don't want a gap here. You want to make sure you have a little line here as well. Okay, so let's go through an example in Orthocubes. This is actually example number 10, and you can see we zoom in and we're going to do the right side view and draw what the right side view looks like, which is almost like a stair-stepping case, and it's that right plane, and there are no hidden lines because the elevation is the same throughout. And then we're going to zoom into the front side view, and you can see that when you're looking directly in front of it, it's going to be tall, but each face is at a different depth. And so we put these horizontal lines to represent that fact. And then when we go to the top view, it's the same thing. When we look from the top, we see that there's, these different rectangles, but they are all at a different depth. So we have to have these horizontal lines. And so then when we submit this, we can see that we got it correct. And let's do another example, and this time it has a hidden line. So we will start this video. And in this case, when we're doing the front view, when you're looking at the full screen, it's a 3x3 object, but behind the scenes, there was a change in elevation at that first line. So you can see we make sure that we have a hidden line crossing the verticals and that we connect against those things. Now on the top view, when we rotate that object and look at the top, we have a 2x3 rectangle, and then there's a change in elevation between those views. And on the right side, we just see an L-shaped object there that's projected, and there's no change in depth along the whole length of it. So when we submit it, that is the answer that we get. So that concludes the lesson on Orthocubes, and you can now try it in the app.